Space is a dangerous place. The Earth is hurtling through clouds of thousands of rocks as it journeys around the Sun.
Any one of them could collide with our planet. And in the past, they have.
So in this programme, we're talking about the awesome power of cosmic impacts.
Welcome to the Sky at Night. We're here at Oxford University Museum of Natural History, home to one of the most impressive collections of meteorites, lumps of rocks which have collided with the atmosphere and fallen to Earth.
Tonight, we're exploring the remarkable ways that cosmic impacts have shaped the universe around us.
Coming up, Hollywood loves the idea of big impacts, but the threat is real. We think that every year, as many as 20 potentially destructive pieces of rock pass so close they travel between the Earth and the Moon. So we're asking you to join us on a hunt for near-Earth asteroids.
Materials specialist Mark Miodownik is here to explain the extraordinary physics that happens when something collides with our planet.
Ready, firing.
We'll be finding out how the biggest impact in Earth's history gave birth to our celestial partner, the Moon.
Most of the Earth probably melted and it would have been left in the state of being a global magma ocean.
And impacts on a truly epic scale. What happens when galaxies collide? But first, impacts that are closer to home. These rocks that we're holding are just two of the meteorites that have come from space into the museum's collection. And on this one, if you look carefully, you can see this crust, and that was formed as this rock plunged through the Earth's atmosphere.
It's estimated that 100,000 tons of material hits the Earth every year. Most of it dust and small rocks that burn up on the atmosphere. And these tiny fragments we see as shooting stars.
But not all impacts are so benign. We know they have the power to reshape our planet, to affect the course of evolution, and maybe even disturb our civilization.
Viewed from space, it's possible to see the scars left behind by collisions in Earth's past. The famous Barringer crater in Arizona was created by a rock just 45 meters in diameter.
The Manicouagan crater in Canada, at 70 kilometers wide, is one of the most impressive craters. It was formed by an impact over 200 million years ago.
Most craters are destroyed by Earth's constantly changing surface. But the Vredefort crater in South Africa is another rare example of a crater that has survived. It was carved out some 2 billion years ago as a colossal 300-kilometre wide basin. The energies involved in these impacts are huge, and it makes the rocks and minerals behave in extraordinary ways.
We asked materials scientist Mark Miodownik to take a look at exactly what happens when an object collides at high speed with a planet.
I've spent my working life studying materials, how they behave and interact. It's a science that underpins the modern world. I mean, everything is made from something. And in an everyday situation like this, we understand how stuff works. We can predict their properties. One thing we've learned is that materials behave differently depending on the conditions. For instance, temperature. If you heat metal up, it gets softer. But if you cool it down, it becomes brittle. And sometimes those differences are extreme. Conditions don't get much more extreme than when an asteroid travelling at over 40,000 miles per hour comes to a sudden stop as it crashes into the surface of a planet or a moon. At these speeds, you enter the world of extreme physics, where everyday materials like metal and rock behave completely differently. Understanding what happens at the moment of impact helps explain the different effects meteorites have when they crash into a planet. I've come to Cranfield University, where the Dynamic Response Group can recreate meteorite impacts in miniature and reveal the key transformations that occur. To see it, we're going to fire an object faster than the speed of sound at a solid target. I've got a lead ball and we're going to shoot it using this high-pressure gas gun. High-pressure helium is going to shoot it down the barrel. It's going to reach speeds of up to 350 metres per second. It's then going to hit the target. It's going to come to a dead stop. And that whole process is going to take about a hundredth of a second. Now, this is a fraction of the speed of a meteorite strike. But even at this slower speed, the energy levels involved are still large enough to mimic one of the key processes at work in asteroid impacts.
OK, Dave, tell me when.
Just about.
Yep.
And as that energy is released, it's going to make solid metal act in an extraordinary way.
Let's go. OK, ready, firing.
Clear?
OK.
We can see the damage. Oh yeah, very nice crater produced by that impact. Have a look at that. Now that is a shape you see all over the universe. And what you're seeing is this material behaving not like you would expect a solid to behave, but actually more like a fluid. Now, all that happened pretty quickly, and even when we slow the footage down 800 times, the moment of impact lasts just a second. The kinetic energy of the projectile, travelling at faster than the speed of sound, has to be absorbed into the target as it comes to a sudden stop, and it's that shock wave of energy that causes the material to flow. This liquid-like behaviour is key to understanding what happens during meteorite impacts, and it also provides another way to study them. So one of the simplest ways of looking at this and exploring the mechanics of asteroid impact is to look at the impacts of fluids. And there's an easy way to do that, which is just to get a pipette and a bowl of water and impact one fluid, i.e. a drop of water, into another, which is the bowl of water. The fact that in the moment of impact solids act like fluids means that you can use something as simple as a water droplet to reveal the processes at work when a meteorite hits the Earth. So here comes the droplet, and as it impacts the surface you can see that immediately it starts to flow. Now of course it does, it's a droplet, but this also happens in rock and in metal, as we saw earlier. But still, you can just see the hemispherical droplet, so half of the droplet in a way doesn't know that the front end has hit. It's still going. The momentum's carrying it forward and off it goes, making the crater deeper and deeper and deeper. The result is that the back of the droplet drives on through the middle, pushing the surface out and up. Meanwhile, the shock wave is making it wider and wider as it comes out. And on the process goes until you get this classic crater shape. It's only because both the surface and the projectile flow that you get this unique shape. Now this looks like it's all finished, but actually the impact is still going on. The momentum of the droplet has gone all the way down to the bottom of the crater, and in a minute will come back up again as it rebounds. There it is. So it's rebounding back up. And the extraordinary thing is you see this effect also in real impacts in asteroids and meteors. We can see it on the Moon, on Mars, and even here on Earth. Now these experiments give us an idea of certain types of impacts and the craters they form, but there are still many types of craters that we don't fully comprehend. Dr. Ken Amor is an impact crater specialist. What are the things we see on the craters of other planets that we don't understand or don't quite make sense?
So the experiments that we do with the gas gun produce a very sort of simple sort of bowl-shaped type of crater. And we can see from this picture here, we have two impact craters. The much smaller one is a younger impact crater. The larger one is a much older one. And this sort of smaller impact crater, it has the classic sort of bowl-shaped, quite a sharp rim. But this is in marked contrast to the much larger impact crater. So you lose this sort of well-defined rim. You've got much more material sort of slumping inwards, forming these sort of terraces. You have a sort of flat-bottomed floor to the crater. And then the thing that we really don't understand very well at all is these sort of central peak type structures. There are a number of theories as to how they might form. So rocks under sort of normal pressures do behave in an elastic way. So it's the bonds between the atoms, so they're sort of being sort of compressed, and then once that pressure is released, they're sort of decompressing, just like a spring, and they're sort of bouncing back. So there's a certain amount of elastic rebound going on, which is pushing up the central peak. But because we can't really generate them in these sort of gas gun experiments, we don't fully understand what's going on.
So you're saying that two different scales of impact, different physics operates, and you get different crater characteristics. Is there a bigger scale still, where you might even get a different, morphology of crater? There
is. So the really large impacts which form the sort of basins, particularly on the Moon, and the really good example is called Mare Orientali. And this has this sort of concentric ring-type structure, very much like a bullseye, over an enormous distance. And so these are the really huge, enormous, perhaps anywhere in the region of sort of 50 to 100 kilometre diameter impactors. Do we know how they form? I mean, is the physics becoming clear? That's really where our sort of physics sort of lets us down. So it would be difficult to sort of reproduce that type of scenario within a sort of gas gun experiment. Very interesting. Thank you.
And next, we're sticking with the Moon. We're used to thinking about impacts as destructive processes, things that vaporise rocks and wipe out dinosaurs.
But impacts can be creative too. And that's especially true for the biggest impact in Earth's history. Something so large that it reshaped our planet and probably caused the formation of the Moon. I've been speaking to lunar expert Sarah Russell about this unique event. Hi Sarah, I'm a lunatic and I love everything about the Moon. So can you tell me how we think the Moon was formed?
Well, before the Apollo missions actually brought stuff back from the Moon, there were three main theories that were around. One was that the Moon was a captured asteroid. So an asteroid just got too close to the Earth and it got captured by the Earth's gravitational field and to form a moon.
And that's how we think many moons form in the solar system.
Exactly. So the moons of Mars, for example, Phobos and Deimos, are probably captured asteroids. But the moons of Mars are much smaller compared to the size of the planet than our moon is compared to the size of the Earth. Another theory is that the Earth and the Moon accreted together, that they just formed, they were always twin planets.
Like a binary system.
Like a binary system, exactly. But that doesn't quite work either because the lunar core is very, very small and you'd expect it to be the same proportion of the Moon as our core is to the Earth. And the other theory is that when the Earth formed, it was spinning so fast that a blob just sort of got flung off the Earth and that went on to form the Moon.
So it's coming off fast enough to be thrown off,
yeah.
But yet it's still enough to be captured.
Exactly.
Yes,
that's
the dynamics of that.
tricky. Yes. But then when the Apollo rocks were brought back and the lunar rocks were brought back by the Russians, we had a chance to look in detail at the chemistry of the Moon rocks, and a consensus started to emerge in the 1980s about how we really think the Moon formed. And we think it formed by this massive collision of a planet about the size of Mars, which is sometimes called Theia, smashing into the early Earth.
So we've got an artist's impression of it here.
So it was a pretty catastrophic event, both for Theia and for the Earth.
What happened to the Earth after that?
Most of the Earth probably melted and it would have been left in the state of being a global magma ocean with bubbling silicate rock covering its whole surface. And then most of the stuff that formed the Moon would have originated from Theia, and that's the stuff that got thrown out from the Earth.
So we have these rocks, you've analysed them. What in the composition is telling us this?
Well, there are a few lines of evidence, but the main one is that the composition of the Earth and the Moon is surprisingly similar, and that suggests that they must share some genetic link.
So you've analysed these samples, just samples returned from the Moon, or do we have any other Moon samples?
Well, since the Apollo missions happened, we actually found out that some samples of the Moon come to Earth naturally in the form of meteorites. And I've got one here to show you. So this one was found in the Sahara Desert, and it's a sample of what we call the lunar highlands, which is the pale part of the Moon. One of the great things about lunar meteorites is that they randomly sample the whole surface of the Moon, so they give us a better idea of the global composition of the Moon, whereas the Apollo astronauts just visited a very tiny proportion of the Moon. So these are fantastic at giving us extra clues about the rest of the Moon.
And by analysing these, we're still finding a high percentage of Earth-like substances.
Yeah, so one of the main arguments in favour of Theia was the similarity between the Apollo rocks and the terrestrial rocks. But actually, geochemists are never happy, and doing more and more analyses, they found out actually they're too similar. They're
Too Earth-like.
They're far too Earth-like, which is actually a problem because the modelling suggests that most of the moon should actually be made of Theia, and by all probability, Theia would have a different composition to the Earth. So could have been a collision of two bodies that were a similar size to each other, and then they would have mixed up more thoroughly. Or it could be that there was a period after the collision where there was a hot vapour that allowed everything to equilibrate and everything to mix up. But this is all research that's ongoing at the moment. But what we really need, Maggie, is to go back to the moon.
I'm volunteering. I want to go.
So if we can get samples, so the problem with the Apollo missions is that they only sampled a very small part of the moon, and the problem with meteorites is that they sampled probably most of the moon, but we don't know exactly where they're from. So we need to go back to targeted areas to get new samples, and then we can solve this problem.
Well, thank you very much, and sign me up.
Thank you, Maggie.
Coming up, how you can help protect the Earth from deadly meteorite strikes by hunting for asteroids that could be on a collision course with our planet. But first, Pete has this month's star guide, including a tour of the spectacular craters on the moon.
Now, when it comes to impacts, there's no better place for amateur astronomers to see their lasting effects than on the moon. There are over 300,000 impact craters, at least 1 kilometre wide on its surface, and many more smaller ones that we're still counting. And on the moon, they're perfectly preserved, frozen in time for us to admire and study. Now, the wonderful thing about the moon is that so long as it's above the horizon, it can be seen at any time and from anywhere. Even here in the centre of London, where it's impossible to escape the city lights, we can still enjoy what the moon has to offer. After new moon, the first phase which allows you to see some surface detail is the waxing crescent. And this is when just a thin sliver of moon is visible in the sky. Now, close to the terminator, that's the line which divides the lunar night and day, that's where you'll see the fantastic shadows which really define some of the craters there. 5 days after new moon, look out for a trio of craters in the southeast quadrant. Called Theophilus, Cyrillus and Katharina, they are easy to see with binoculars. As the nights pass, the terminator sweeps across the lunar landscape, revealing more of the moon's surface to us. At first quarter, the moon appears in the sky as a half circle, and in the following days, 2 really impressive examples of a distinctive type of crater become visible. These are Tycho and Copernicus, and they're ray craters, and they're really quite spectacular. These spider-like patterns of bright rays can extend for hundreds of kilometres. They form because at the moment of impact, light-coloured material from underneath the surface is pulled up, creating the streaks. Finally, 2 weeks after the new moon, we arrive at the full moon. Now, this is when the full face of the moon is illuminated, which is what we've got tonight. Now, when that occurs, the sun's light falls straight down onto the lunar surface, and there are no shadows cast, so it's really difficult to make out any crater detail. But there is something else which is on view. A huge circle of dark lava covers the northern hemisphere. It's over 1,000 kilometres wide and at least 3 billion years old. It's called Mare Imbrium, and though it looks very different to the classic craters we've seen, it is in fact a giant impact basin, one of about 40 dark basins that litter the moon's surface. And there are lots of other great things to see this month besides the moon. So here's this month's star guide. It's a great time of year to see the Milky Way. The 3 bright stars, Deneb, Vega and Altair, form a large pattern known as the Summer Triangle. This is visible towards the south, roughly 2/3 of the way up the sky during June. Deneb is the brightest star in Cygnus, a constellation with another distinctive pattern in its centre known as the Northern Cross. If you have dark skies, look out for the Milky Way passing down the length of the cross. The Milky Way is the merged light of billions of distant stars in our own galaxy, too distant to be seen individually with the naked eye. Dark dust blocks this delicate light in Cygnus, and the Milky Way appears to split in two. The split is known as the Cygnus Rift, and it's a magnificent sight in a dark sky.
When we think of impacts, we tend to think of our own solar system. But of course, collisions are happening throughout the universe on many different scales. Chris is speaking to cosmologist Karen Masters about perhaps the biggest collisions of all, when galaxies collide.
When we look beyond the Milky Way at other galaxies in the universe, we see that often these enormous structures are moving together. And in some cases, we can catch them in the moment of collision. We think that this is an important part of how the universe evolves and a trigger to make stars form. Well, we're here to talk about collisions, and perhaps the most spectacular of all is going to happen to the Milky Way in a few billion years' time. So what's going on?
The universe is expanding, but gravity is always acting. So, for example, the Milky Way and the Andromeda Galaxy, our nearest large spiral neighbour, the gravity between those two galaxies are pulling them together, and we believe they're going to collide and merge sometime about 5-6 billion years from now.
So that sounds spectacular,
Yeah.
but what does it actually mean for our galaxy? What happens to the Milky Way when it undergoes such a merger?
So the distances between the stars and galaxies are vast compared to the size of stars. So as the galaxies merge and collide, no two stars are ever gonna hit each other, but the combined gravitational action of all of those stars moving together, they distort the galaxies, they pull out these amazing tidal arms and tidal tails, there are bridges built between the galaxies.
Well, you brought along a simulation of the future of the Milky Way, so here we are. This is the Milky Way, right?
Yeah, so this is a visualization where they've simulated two large spiral galaxies. That one's the Milky Way, and here we have the Andromeda Galaxy. The gravity between these two galaxies is pulling them together, and it takes a few seconds in the movie, but in reality it's going to take about 5 billion years. You're going to see all sorts of structures shooting out of them. So you see these tidal tails and bridges. Beautiful long arms. These are all the stars from these galaxies being thrown out of the galaxy by the gravitational interaction.
But you end up with something rather boring.
Yeah, that's right. So the product of all of this merging tends to be rather spherical in shape, rather boring, the elliptical galaxy.
What about the sun? What will happen I mean, imagine we're still here in 6 billion years.
Yeah.
I'm sure the sky at night will still be going. So,
Yeah,
so what should we be expecting to see, and what happens to us?
The sun will either remain in this remnant, so it will become part of an elliptical galaxy, or there's a small chance, something like 10%, that it will get kicked out into intergalactic space.
Rather sober thought. Has it happened to the Milky Way before?
We know the Milky Way cannot have had a major merger, where the thing that merged with it was comparable in size to the Milky Way itself in the last 10 billion years, because it has an incredibly thin disk. And so you can't sustain that kind of thin disk in a major merger.
Because a merger would inevitably kick stuff up out of the disk.
That's right, yeah. It kicks stuff up out of the disk. It will drive stars and gas into the centre of the galaxies and build the bulge, the spherical egg yolk component of the galaxy.
And there are other important effects as well. So we've seen the change in the shape, but we also get things like star formation within the galaxies.
Yeah, so galaxies aren't just made of stars, they also have quite a lot of neutral hydrogen gas, the kinds of the fuel for star formation. And when the galaxies collide, those gas clouds can be put under pressure, and that pressure can induce star formation. And so we see bursts of star formation in galaxies that are colliding.
And this is something that astronomers have changed our minds about over the last few years. It's tempting to say, look, stars form in major mergers, and therefore most stars must form in mergers, but that doesn't seem to be the case.
No, it makes a very nice story, I think, very simple story. But these processes that compress the gas clouds that happen in mergers can happen due to other effects going on in the galaxy, the effects of the spiral arms, the gas clouds kind of ride on them like surfers riding on waves in the ocean and compress things and cause star formation. So you don't need a major merger to form stars.
Karen, thanks a lot.
Now, closer to home. We want you to join us on an asteroid hunt. The aim is to discover near-Earth asteroids that have never been observed before. Objects that are close to our planet or cross its orbit and could potentially hit us.
Now, history has shown that in the past, meteor strikes can have a devastating effect on our planet, like the ones that struck at the time of the dinosaurs.
65 million years ago, a meteorite 10 kilometers wide crashed into the Earth. It unleashed an Armageddon on our planet, resulting in a nuclear winter that blocked out the sun for decades. The impact led to the loss of 3/4 of all species alive at the time. What I have in my hand is evidence for that impact, and it's one of the most remarkable things I've ever seen. This line here marks the point, the exact moment at which the asteroid that did for the dinosaurs hit the Earth. And up here above it is clay infused with iridium. That iridium is the fallout from the meteorite. It came from space. But what's really remarkable is that this rock doesn't come from Mexico, where the impact occurred, but from Copenhagen, more than 5,000 miles away, showing that the asteroid changed the future of the entire world. But such big impacts are rare. Maybe they happen once in a billion years or so. And so what should concern us now are the smaller impacts.
Because even the small ones can be dangerous. We are constantly being bombarded by rocks, small by astronomical standards, but big enough to create explosions, with a kind of force associated with nuclear weapons.
Since the year 2000, a network of sensors have been monitoring the planet with the aim of detecting nuclear explosions. In that time, it's detected 26.
These apparent explosions range in force from 1 to 600 kilotons. That's 40 times the power of the Hiroshima bomb. But none were nuclear weapons. They were all asteroid impacts blowing up in the upper atmosphere. They reveal we are being bombarded at an alarming rate, at least 3 times more frequently than previously thought.
All this demonstrates why predicting when and where a meteor might hit the planet is so important.
We think we found most of the large ones, but even the smaller asteroids could take out a city. The first step to protecting ourselves is to find them and track them. And so far we've managed to trace the orbits of 10,000 near-Earth asteroids. But that's less than 1% of the city killers that might be out there. Asteroids bigger than 30 meters, which would hit the Earth with all the power of an atomic bomb.
So we need to find more, and that's where you come in. We want to harness an ability that you have that beats most computers, the ability to detect movement.
A special website's been designed based on images compiled over 20 years by the Catalina Sky Survey. Each patch of sky is imaged multiple times, normally 10 minutes apart. And most things in the sky don't move on that timescale, but near-Earth asteroids will. And so if you see something moving, you might just have caught one. So go to asteroidzoo.org or to the Sky at Night website to find out how you can participate. Every image you see will also be checked by several other volunteers, and we hope to follow up on the best targets with our telescopes.
It's really easy to take part, and we'll report back on what you've found in the next few months.
So that's it for this programme.
Next month, we'll be looking at what seasons are like on other planets in our solar system and how it's possible to do stargazing in the middle of the day.
Our website at bbc.co.uk/Sky at Night contains details of everything we've talked about on today's programme, as well as details of more than 600 astronomical events happening all over the country.
In the meantime, get outside and get looking up.
Good night.
Stay with us, more stargazing coming up as Horizon gives us a guide to the red planet. That's here on BBC4 in just a moment.